Hello friends, I'm going to talk to you about principal stresses. Principal stresses is a topic which if you do not understand, you will not be able to understand a number of other things like 3D stress analysis, 3D failure criteria, etc. This is one of the most important concepts in mechanical engineering, uh, mechanical engineering stress analysis, and it is essential for mechanical engineers to understand it. So it is taught in the undergraduate courses itself. Uh, and also, if you see the failure criteria for brittle materials, it is this principal stresses. Maximum principal stress is the failure criterion for the brittle materials. So if you do not understand this, you are at a profound disadvantage, especially if you are a stress analyst. If you like this video and want to view similar content, do subscribe to my YouTube channel. I have said that this is an important concept, but if you try to learn it by opening a textbook and reading through it, you will realize that a lot of mathematics is used, which can be a little bit irritating for many people, including many stress analysis engineers. So, what I'm going to do in this video is that I'm going to try to explain to you in a simple way without using too much of mathematics. So, consider a bar like this, which is fixed at one end and somewhere close to the free end, not at the free end, close to the free end, we have a load of 1000 newtons applied as a transverse load. So the length of this bar is 100 mm, the width is 15 mm, and its height is 10 mm. So let us analyze this problem. Now let us cut the body at an inclined plane at a point A and check the resultant of the stresses at point A. How do we do it? So simple. We take the point and we take a very small area around it and we multiply it, and we multiply the area by the stress induced in that area. That way we'll get the force. And since it is force which is a vector, you have to consider the direction also. So we are going to see at different points and at different planes how the force varies. So we are going to do this for different points and different planes, but we are going to do it non-mathematically. So mainly what we are going to see is the inclination of the stress resultant force with respect to the inclined plane. So that is going to be our main intention. On screen is the problem that I had earlier described. The same bar fixed at one end and somewhere close to the free end we have 1000 newtons applied as a transverse load. So I'm going to take 3 points here, A, B and C, which are indicated by the red dots, and we are going to cut through these points by an inclined plane. So the plane of cut you can see, right, shown by dotted line and arrows. So that we are going to use as the plane through which we are going to cut. So, and you can see what I mean by point. By point here I mean the shaded area, as you can see in the figure in the second figure that is there below. So the shaded area is what I mean by point. So this is a 2D analysis, so we are going to assume that the stress does not vary along the width. So this is a 2D plane stress problem. I'm showing you the 3D picture so that you understand what I mean by point. So here we will calculate stress according to the beam theory. So this is a problem that is appropriate for beam theory. And so let us do it. Let us calculate the stresses by beam theory. We are going to calculate both the bedding stresses, which are normal stresses, and also the shear stresses. So here you can see that the point A is in pure tension. There is no shear at that location. So there is only tension at that location. So point A is in pure tension. Now let me show you visually the direction of the stress resultant and the plane. So you can see the tension is along the horizontal direction but the plane is inclined at 45 degrees to the horizontal. So you can see that the direction of stress resultant is not perpendicular to the plane. So this is not a principal plane. So at the principal plane, the direction of the stress resultant will be perpendicular to the cutting plane. As I had discussed, there are 3 points we are going to analyze: A, B and C, and you can see A and B are highlighted. So I'm going to do the analysis of stress for points A and B, and I'm going to leave the point C as an exercise for you. So we have taken a plane inclined at 45 degrees and we have understood that it is not the principal plane. Now let us take a vertical plane as a cutting plane and let us see the direction of the stress resultant with respect to the plane. So you can have a look at the direction of the resultant, and also on the right side you can see what I mean by the point. The point means the shaded area. So that is the stress area that is shaded, and that is what I'm taking as the point A. So you can see that the direction of the stress resultant is perpendicular to the direction of the plane of cut. So this is a principal plane for us. By definition, the principal plane is the plane on which the direction of the stress resultant is perpendicular to the plane of the cut. Now that we have found the principal plane for the point A, now let us move on to point B. I hope by now you have understood what is meant by the principal plane and what is meant by principal stress. So principal stress is nothing but the stress on the principal plane. So now let us move on to the point B. Point A, we had seen that the vertical plane was the principal plane. Now let us check out if it is also the principal plane for point B. So point B is in pure shear, and the direction of the stress resultant for this vertical cutting plane is downwards. So it is not perpendicular to the cutting plane, instead it is parallel to that. So this is not the principal plane. Now that we have seen that the vertical plane is not the principal plane for point B, we will take a plane inclined at 30 degrees to the vertical and see if this is the principal plane for point B. So we can see that from the figure on the screen, the stress resultant shown by the black arrow is not perpendicular to the plane of cut. So this 30-degree plane is also not the principal plane for point B. And I would like you to notice one interesting phenomenon. So the direction of stress resultant has changed from the previous plane. See, when the plane was vertical, the direction of the stress resultant was downwards. Now that we have changed an angle of the plane of cut, so the direction of stress resultant has become inclined, right? So why did it happen? So we did not see such an effect at point A. At point A, irrespective of the angle of the plane of cut, it was always horizontal. Here, why is it changing directions? The reason is that point A was in pure uniaxial tension. So irrespective of the plane of cut, it was it was horizontal. So the direction of stress resultant was horizontal irrespective of the inclination of the plane of cut. But at point B, it is in shear. So what happens? Shear is accompanied by complementary shear. So in the pure sense of term, shear cannot be uniaxial. So what happens? As you change the inclination of the plane of cut, the direction of the resultant will also change. If you want to understand this, I'm afraid you have to try it out mathematically and see for yourself. Now that we have realized that the plane inclined at 30 degrees is not a principal plane, now let us try a plane inclined at 45 degrees and see if it is the principal plane. So now you can see that the stress resultant is perpendicular to the plane of cut. So this is the principal plane for point B. And I want you to observe that the direction of the stress resultant has changed again. In the figure on the right, you can see the stress area for point B for this particular plane. It is shown by the shaded region on that inclined surface. So this is not to scale. So ideally, the shaded region should be as small as possible. This is just to show you qualitatively. So if you take the principal plane, the plane perpendicular to the principal plane is also a principal plane. So one of them will have the maximum stress and one of them will have the minimum stress. So in 2D you have two principal planes and two principal stresses. In 3D you will have three principal planes and three principal stresses. I leave point C as an exercise for the viewers. So from this qualitative analysis that we have done, so let me tell you the observations. The planes on which the shear stress is zero are called principal planes. So why? Because if the stress resultant is perpendicular to the plane of the cut, there will be no shear stress. Next, the normal stress is maximum on the principal planes and is called principal stress. So similarly, we also have minimum principal stress in 2D. So maximum minimum in 2D, and in 3D we have maximum minimum and principal stresses. So different points in the body have different principal planes. As you could see, the point A and B did not have the same principal plane. So point A it was the vertical plane. Point B it was a plane inclined at 45 degrees to the vertical. So the plane, the principal plane varies from point to point. So the next thing is the plane perpendicular to the principal plane is also a principal plane. So in that also the stress resultant will be perpendicular to the plane of cut, and the shear stress will be zero, obviously. So in the 2D we have two principal planes, and in 3D we have three principal planes. Thank you. In this video, I have discussed about the principal planes, and I hope this helps you to understand the concept. If you like this video and want to view similar content, do like and subscribe to my YouTube channel. Thank you.